How far can we push the Big Bang model? In a sense, science makes progress by trying to break theories. As Nobel Prize-winning physicist Richard Feynman once said, we're trying to prove ourselves wrong as fast as possible, because that's how we make progress. So rather than resting on their laurels, cosmologists are trying to test the Big Bang theory in new ways and in new regimes. The frontier of cosmology involves the very early universe. How far back towards the Big Bang can we push our physical theories? There are various landmarks in the history of the universe, and there are places in the chronology we think we can access with observations that represent extraordinarily early instants of time in the history of everything there is. In terms of current theory, the frontier of knowledge is what's called the Planck Era, an amazing 10 to the minus 43 seconds after the Big Bang. Conceptually, this is a time in the infant universe when space itself was as curved as a particle, when the distinction between space and time did not exist, or the objects in space and the space that contained them. This was when the universe was smaller than the smallest subatomic particle. Our physical theories break down at this point. We can only understand the universe at the Planck time if we have a theory that unifies all the forces of nature. This is the famous quantum theory of gravity that Einstein struggled to create for 20 years and failed. Since then, very smart physicists have been working on the theory, and no unique theory has turned up, but there are some that are getting a lot of attention. But at the moment, this is the frontier. Physicists and cosmologists are motivated to work back towards the first instant of creation by the fact that unification is a powerful idea in physical science that has had many successes in the last few decades. There are four forces of nature that in the present-day cold and vast universe have completely different strengths, ranging over 38 orders of magnitude. And there's no explanation for this in the standard model of particle physics. Hints that all of these forces may be manifestations of an underlying superforce come from high-energy physics. In the 1970s, experiments at the particle accelerators at CERN showed that the electromagnetic force and the weak nuclear force, which causes radioactivity, were manifestations of the same thing. At the energies reached by CERN, particles were found that mediate both forces, but at lower energies these forces are distinct. This unification, the so-called Electroweak Force, led to the award of several Nobel Prizes in the late 1970s. Encouraged and emboldened, physicists speculated that at even higher energies, the next strongest force of nature, the strong force, which holds together nuclei, essentially the gluons that hold quarks together and protons and electrons, would also be unified with the electroweak force. But what we knew about high-energy physics suggested that this unification would not occur until an incredible temperature of about 10 to the 28 or 10 to the 29 Kelvin. Very high temperatures must all have been present if we go back early enough in the history of the Big Bang. So the testing ground for this kind of physics comes only from the Big Bang. This is the grand unified theory that is the basis for the inflationary model in cosmology. Beyond the grand unified theory is the speculation that gravity is brought into the fold at even higher temperatures, and of course even earlier times in the Big Bang, and that's the Planck Era, the limit of all physical knowledge. Just thinking about the Big Bang, it's an extraordinary event. 100 billion galaxies and the 100,000 billion stars they contained were all compressed into a space smaller than a subatomic particle. What the Big Bang theory really says is that Genesis was a quantum event. The universe itself was created in a quantum event, and that's the physical state we're struggling to understand in cosmology at the moment. What we need is a theory of everything, which is to say a grand unified theory of the four forces of nature, the theory that eluded Einstein for so long and other smart physicists since. If the inflationary part of the Big Bang theory is verified by observation, we will have direct evidence that the universe started from a quantum state. The exponential expansion of inflation essentially blew up quantum fluctuations to macroscopic size, where they would subsequently become the seeds for galaxy formation. That same expansion, of course, is responsible for the flatness and smoothness of space. Whatever the initial curvature, and it must have been extreme, space has now been inflated to an enormous size where space curvature in any large region is negligible. This idea puts the microwave sky in a whole new light. What it says is that when we look at the microwave background radiation through a radio telescope, we're looking at quantum fluctuations writ large on the sky, the seeds for galaxy formation. At the time we see the microwave fluctuations, their amplitude is just a few parts in 10 to the 5. But from those tiny acorns, big oak trees eventually grew. Over a period of a few 100 million years, they grew and amplified, became nonlinear, and then gravitationally collapsed to the stars and galaxies we see in the universe today. Cosmologists are pushing the Big Bang theory towards its limit, the origin of time and space itself, the first fraction of a second after the Big Bang. But to do so, they need a unified theory of the four forces of nature. We don't currently have such a theory because no one's been able to successfully reconcile general relativity and quantum mechanics. But in this unification, it appears that quantum space-time foam led to all the space and time that surrounds us, containing 100 billion galaxies.